All right, cool. Well, welcome back. In the second part, we're going to actually carry out the reduction to biclustering. Before we do that, I'm just going to briefly explain one other really nice thing that's true about the definition of reduction in total variation. So this reduction, again, just to remind you, the definition of reduction is saying that we have an efficient algorithm A that takes the H0 instance of problem P, maps it to the H0 of problem P prime with some error epsilon, and similarly for H1. So suppose that A is mapping some distribution P to P prime with error epsilon, but suppose that we don't actually have an instance of distribution P. We actually have something else. I'm going to write this as approximately sub delta. We actually have P tilde. Okay? So the reason why this will be true will become obvious in a moment. It'll be because this P or P tilde is actually the output of some other algorithm or some other reduction that's approximate. So what's true is if you, instead of feeding into the algorithm a sample from P, you feed it something from P tilde, then that still approximately maps to P prime, but the error now is epsilon plus delta. Right, so what this is saying is that you don't even need the input to exactly be the thing you hope it is. It can be something that's close, and then your output will still be close where it's now an added delta distance. Okay, so the reason why this is true is because this is saying that the TV is less than or equal to delta, which means that there exists a coupling that makes the sample from P and the sample from P tilde literally the same, except with probability delta. And so the behavior of the algorithm is going to be the same, except with probability delta. And so as one kind of pushes through the coupling interpretation of TV, you can sort of quickly derive this consequence. Any questions on that? I'm happy to go through it in gory detail, but hopefully it at least makes intuitive sense. All right, so there's a further consequence of that, which I'll write as a lemma, because it's very useful. So that's if A is equal to the composition of A2 and A1, and A1 maps P to P1 with error epsilon 1, and A2 maps P1 to P2 with error epsilon 2, then the composition maps P to P2 with error epsilon 1 plus epsilon 2. Right, so things behave very nicely under composition. And we can prove this. So why is this? Well, if we unpack what this starting thing is saying, it's saying that A1 maps P to P1 tilde, which is epsilon 1 away from P1. Right, that's what this arrow sub epsilon 1 means. Okay, but then we can look to the upper half of the screen and we see that A2, well, again, this is part of the assumption here, that A2 maps P1 with error epsilon 2 to P2. And then we look to the upper half of the screen and we conclude here that A2 maps P1 tilde to P2 with error epsilon 1 plus epsilon 2. Right, so that's the proof of the lemma. And so why this is useful is that we can now think about algorithms as having sort of subroutines, as operating sequentially. And we can, at any intermediate point, pretend that we have the distribution that is some sort of idealized thing that we wish it was, and just kind of in a comfortable way, just add up the epsilons, which are the various errors along the way. Put another way, if our reduction is most easily analyzed with some input that's close to what the input is actually going to be, we're free to just do that. Okay. So this is critical for the analysis, and it'll probably be pretty clear why. Okay, so here's the theorem that I claimed. We're going to map planet clique to biclustering, in particular this hard region to this other hard region. Question? No. Okay, so we're going to do this in two parts. We're first going to map the hard region of planet clique to this bottom edge of the triangle. And then we're going to map this corner of the triangle upwards along this right edge to then conclude that everything along this right edge is also hard. This is kind of two separate reductions, two separate arguments, and it's already going to make use of this kind of composition of algorithms, composition of reductions argument. Okay, so before we fully dive into what this reduction looks like, let me draw some pictures. So consider H1, the planted case of both. And that's a terrible square, so let me redo that. So here's a square. It's going to be the adjacency matrix of planted clique. So it's symmetric, has ones in some block of vertices, which are the planted clique. And then everything else here is Bernoulli half. So that's what a input, a sample from planet clique looks like under H1. And what we're trying to do is to map this to something that has normal lambda 1 and normal 0, 1, or Gaussian 0, 1. Okay, so there are a few different differences between these two distributions. The first is that we need to map the distribution of the entries. So this is Bernoulli half, kind of everywhere in this matrix. And we really want to map this to standard Gaussian, which we'll denote by Q. And then the 1 from the clique entries, we want to map to P, which is just going to be shorthand for Gaussian with mean lambda. So that's kind of the obvious difference between biclustering and planet clique, because this one has 0, 1 entries, this one has Gaussian entries. All right. And I'm going to just call this change of distribution. Okay, now the second problem is that the diagonal of the adjacency matrix is missing, because those would correspond to sort of self-loop edges. Those are missing. And so we need to add in the diagonal somehow. And also, we only have independent entries in the upper triangle because, I mean, that's an undirected graph, right? And so we need to remove the symmetry. We somehow need to arrive at a matrix that has all independent Gaussians. It's not a symmetric matrix. Okay, so these are actually three separate things that we need to try to do. And we're going to have a separate reduction for each of them. And the composition thing from a moment ago is going to allow us to just separately analyze each of these. So let's start with the change of distribution. So we're going to map 1 to a sample from P. And the reason why that makes sense is, well, we need to map the clique to Gaussian with mean lambda. So let's just, every time we see a 1, let's just sample Gaussian with mean lambda. And that's going to be good enough because the clique will get mapped to this submatrix, right, with this distribution. If we see a 0, then we're going to sample from some other distribution, nu. So then the question is, well, what in the world should nu be? What's a good choice for nu? Well, we know that we would like to map Bernoulli half to Q. So what does Bernoulli half get mapped to? Well, with probability half, we see a 0, and then we draw a sample distributed according to phi of 0. And with probability half, we see a 1, and then we output phi of 1, which is sampled according to P. So the distribution here is the half-half mixture of nu and P. This makes sense. If the input was Bernoulli half, then with probability half it's 1, probability half it's 0. Our algorithm does something if it sees a 0, it does something if it sees a 1, produces a sample from a different distribution, nu or P. And so then the output distribution is the half-half mixture of nu and P, the output distribution of that particular entry. Okay, so the hope, we're really hoping that this is equal to Q. Okay, and just to emphasize, why are we hoping that it's equal to Q? Well, we're gonna apply this map to every single entry of the input adjacency matrix. We're gonna get then some matrix at the output, and we're hoping that all the Bernoulli half entries get mapped to standard Gaussian, right? And all the clique entries get mapped to Gaussian with mean lambda. Okay, so we're hoping that this is equal to Q, and so now we can just do some linear algebra, and we can conclude that nu should be equal to what? 2Q minus P. Seems pretty good, right? Because if you plug in 2Q minus P into nu, then indeed, this half-half mixture is equal to Q. So what do you think? Anybody see any issues with this? Any objections? Yes, please.
Do we know if it's a broker basically?
Good. So just to be clear here, Q and P I'm using to denote the densities of the Gaussian with mean 0 and mean lambda. And the observation is, well, it's not super clear that 2Q minus P, so we're looking at the difference of some densities, is actually a density. So in particular, if you draw it, well, it actually looks like this. So Q here is Gaussian with mean 0, P is slightly bigger mean, and then in blue here is 2Q minus P, and we see that indeed it goes negative, and densities aren't allowed to do that. This is somewhat of a bad situation because we can't produce a sample from 2Q minus P because it doesn't even mean anything. Turns out there's a simple fix, and the fix is to consider the part of the line where 2Q minus P is non-negative, and then truncate that whole thing, and then sample from the distribution that is proportional to that. So in order to define that new distribution, let omega be exactly those x's such that 2Q minus P is non-negative. It turns out that when mu is pretty small, like 1 over root log n or 1 over 10 root log n or whatever, then this point at which 2Q minus P becomes negative is roughly 1 over mu, and so it's going to be a constant times root log n. So that's a calculation that you can do just by setting 2Q minus P is equal to 0 and solving for x. Just using the form for the density of a Gaussian. Okay, so this is this interval, and it's goes from minus infinity to, let's say, 3 log n with the square root there. And so then we can let nu equal to Q minus P normalized by something, z, and then times the indicator on omega. Right, so this ensures that it's always going to be non-negative. Z ensures that this thing is normalized so that it integrates to 1, and so then it's indeed going to be a valid density. Okay, so at least now we're sampling from a valid density in the case that we see a 0. Of course, now the problem is that the half-half mixture of nu and P isn't what we hope it is. The only thing that might save us at this point is if it's just very, very close to what we hope it is. And so the lemma is that indeed that's the case. So the lemma is that the total variation between the half-half mixture of nu and P relative to Q is little o of n to the minus whatever you want. Let's just put a 3 there. If mu isn't too big. So let's say square root of 6 log n. Okay, now this half-half mixture, this is exactly the distribution of what we produce when we see a 0. So it's phi, the distribution of phi is 0. And so this is telling us that when we see, whoops, sorry, that's not the distribution of phi of 0. That's the distribution of phi of Bernoulli half. And so this is telling us that indeed the Bernoulli halves get approximately mapped to the standard Gaussian. All right. I was going to go through a sort of careful proof of this, but I don't think that that's maybe the most illuminating thing in the world. I can, if you want a hint, I can say that the key to kind of a slick proof of this is that z is 1 plus little o of n to the minus 3. And so this rescaling factor is extremely close to 1. And so by truncating this distribution, we haven't really done a whole lot. Now, the intuitive reason why that's true is because both Q and P have very little mass to the right of the threshold point. So if neither of them has almost any mass, then 2Q minus P also has almost no mass, and it's just pretty much irrelevant that we chop the distribution up there. Okay, so you'll just have to believe me that this lemma is true. But again, it's actually a pretty simple calculation that you can just write down from the sort of L1 metric perspective on total variation. So it's just the integral of the absolute value of the difference of those things. And then you can just partition the integral onto omega and omega complement, and it works out. All right. Cool, so maybe I'll state one more lemma, which is that if, well, okay, the purpose of the next lemma is to transfer this bound, which is on a single entry. So we're mapping a single entry of the adjacency matrix to the target matrix. But really, we care about the entire matrix and the joint distribution over the entire target matrix. And so how does one transfer this statement about a single entry to the entire joint distribution over the target matrix? Well, total variation turns out to tensorize in a nice way. And so if x1 is independent of x2, that's what this sort of orthogonal symbol is supposed to denote, and y1 is orthogonal, sorry, is independent of y2, then x1, which way am I doing this? x1, x2, right? So x1, x2, we can consider the total variation to y1, y2, and it turns out that it's less than or equal to the sum of the total variations. So we're trying to distinguish x1, x2 from y1, y2. And the distance between these turns out to be upper bounded by the sum of the distance sort of on the first coordinate plus the distance on the second coordinate. This is almost an immediate consequence of the coupling interpretation of total variation. So I'll leave it to you, but this is extremely useful because now if we care about the total variation distance of the entire output matrix relative to what we wish it was, that's upper bounded by the sum of the total variations. And there's at most n squared entries, and this bound on the TV is n to the minus 3. And so we're in good shape. So we correctly map actually the entire joint distribution. Okay. Cool, so if we go back all the way here and we look at our sort of intuition about what is different from the distribution we're trying to produce and the one that we have, well, first we have this change of distribution, and we've just finished going over that. So we've successfully mapped Bernoulli half and 1 to standard Gaussian and Gaussian with mean lambda. We had this additional issue, which is that we don't have a diagonal, so we need to have a diagonal. We also have a symmetric matrix, and we want a matrix that doesn't have any symmetry, where we have independent entries everywhere. So I'll tell you how to overcome the symmetry thing first, and the diagonal we'll do kind of at the very end. Yeah, you'll see why the flow of reasoning is best this way. All right, so the way that we're going to remove the symmetry is we're going to create additional randomness. And the way that we're going to do that is by something called Gaussian cloning. It's called also Gaussian sample splitting. It's called various things, but it's a very simple idea. And so here's the lemma that describes what this procedure is. So the lemma says there exists an efficient algorithm, C, for cloning, that takes in a single scalar and produces a pair of scalars such that if the input is a Gaussian with mean 0, now you get 2 Gaussians with mean 0. If the input was a Gaussian with mean lambda, now you get 2 Gaussians. However, the mean is no longer lambda, it's lambda over root 2. Okay, so you input a single Gaussian, you output 2 Gaussians. You can't get something for nothing. So in the case that there was mean lambda, the mean shrunk a little bit. All right, so why is this going to help us to remove the symmetry? Well, maybe I don't need to write anything at this point, but we have a matrix that only the upper triangle is meaningful, so we can map that to the Gaussian problem. And then we can just clone it and get 2 triangles. And so one of them will be the lower triangle, one will be the upper triangle. All right, so what's the proof of this cloning lemma? So here's the algorithm. It's going to input x, which is a sample with mean lambda. I'm just writing it like this because lambda could just be anything. And I mean, I could have just written the second thing because you could have taken lambda equals 0 because this holds for any lambda. So that's step 1. Step 2 is sample z, which is standard Gaussian independently of everything else. And then finally, we're going to output 1 over root 2, and then the pair x plus z and x minus z. So why is this going to be what we want? Well, this is 1 over root 2 times the matrix 1, 1, 1 minus 1, and then vector xz. Right? And while x is a Gaussian with mean lambda, so this is equal to lambda plus standard Gaussian. And so if we write it like that, we can separate out the mean and we get 1 over root 2, 1, 1, 1 minus 1. And then this is lambda 0, and then plus, same thing, 1 over root 2, 1, 1, 1 minus 1. And then here we have a pair of standard Gaussians. All right, so if we look at the first term, then this is exactly lambda over root 2, lambda over root 2. And what is the second term? Right, we have a 2-dimensional isotropic Gaussian. So I heard 2 times Gaussian with 0, 1, 0, 1. So I think it's close. So I claim that this is, again, exactly a pair of standard Gaussians. Right, and one way to see that is that if I call this matrix, I don't know what we should call it, let's call it B or something, then thinking of this as a multivariate Gaussian, this is just going to have covariance matrix B transpose. But B is an orthogonal matrix, so this is equal to identity. And well, that's that. We have multivariate Gaussian with identity covariance. Everybody okay with that? Okay, yet another way to see this is that if we just have 2 standard Gaussians, this is, if you were to plot the density, it's like a, I don't know, like a volcano thing, right? And it's rotationally invariant. And this matrix B is just a rotation matrix. So this is the same distribution because we just rotated something that's rotationally invariant. Okay, well, anyway you like to look at it, this proves the lemma because we now have our 2 Gaussians with mean lambda over root 2. Okay, so that's Gaussian cloning. And it's useful in fixing this symmetry issue. So here's the whole reduction for that like bottom part of the diagram. So basically, we're just Gaussianizing by mapping using this funny distributional map that was almost 2q minus p, and then there was this argument to show that the total variation didn't really, we weren't too far in total variation. Then we can just clone the thing and symmetrize it. And so instead of just having an upward triangle, we now have both. Okay, then we have this diagonal, which is another major issue. And what we're going to do is we're just going to put the entire diagonal to be standard Gaussian. Now, that's a wrong thing to do. It's fine for all of the entries that aren't the planted ones. But if we zoom in here, then we see that we've put blue entries, standard Gaussian entries, on the diagonal in the planted k by k thing. So this is definitely just the wrong distribution. But it turns out that after permuting, it's undetectable that those are blue instead of purple on the diagonal. And so I'll state a lemma in a little while that shows that that's indeed the case. Now, if there was no purple thing, if there was no planted submatrix at all, then of course it's totally fine to just put a bunch of standard Gaussians there to fill in the diagonal. That's exactly the right thing. Turns out it's also fine, even if there is this planted thing, because those are somehow relatively very few entries. Okay, so we'll return to that in a little while. And the reason we're going to return to it is because I want to talk about the other part of the hardness diagram, which is actually the more interesting one. And so what we're going to do is we're going to start with the point here. So this is k is square root of n because alpha is half. And what we're going to do is we're going to move upwards along this trajectory. And we will arrive at any point that we want on this right side of the triangle. And the reason why we need to do this is because so far we've only shown hardness down here. Conceptually, why this is significant is because for the first time now, we're actually going to change k. We're going to change the size of the planted structure. So that's significant. We're somehow departing in a mild but significant way from planted clique. And conceptually, what's happening is we're growing the size of the planted structure, and we're optimally trading off with the strength of the signal. Planted clique has no signal strength. And so now we see that the signal strength interplays in an interesting way with the size of the planted signal. Now, some of you may object to the statement that planet clique has no signal strength, and for good reason, because it's actually just complete garbage. You can introduce a signal strength in planet clique, not by varying the strength of the clique, because there's nothing to do there, but by changing the strength of the ambient edge density. So if you make the ambient edge density get very close to 1, it becomes harder and harder to find the clique. And it turns out that there's a phase diagram that actually looks identical to this one. All right, so that's an aside. With that, we'll try to understand how do we move along this edge of the hard triangle. Okay. Oh, I guess I'm just gonna do it myself. Perfect. Oh yeah. All right, so what are we doing here? Claim is that there exists an algorithm. It takes an instance and it kind of moves it along this triangle. And so I'm gonna describe how to do that. So the first thing is that we should describe this trajectory. What is this trajectory? Well, it's k squared lambda over n is kept constant. So if we keep k squared lambda over n constant, that tells us that we're appropriately trading off between the strength of the signal and the size of the planted signal. We're trying to grow k. Inevitably, we're going to lose something in the signal strength, and this will tell us that we're doing the right thing. Okay, so here's now our instance of the problem. It's n, there's a k by k planted thing in there. This is Gaussian with mean lambda. This is Gaussian with mean 0. And what we're going to do is we're going to take every single entry of this input matrix, and we're going to do this cloning to get 4 entries. If we had a planted entry, then we had mean lambda, which gets mapped to lambda over 2. Right? Because we lost a factor of root 2, but then we cloned twice to get 4 entries. N becomes 2n, and then k becomes 2k. So now we can check, did we keep k squared lambda over n constant? Well, let's just plug in. We can do that over here. So we have now 2k quantity squared, lambda over 2, and then 2n. And we can see that that's equal to k squared lambda over n. All the 2's cancel. Right, so that's it. This reduction is very simple once you know about the cloning thing. One thing that's a little weird, by the way, if you're not familiar with this sort of thing, is that we actually, in some sense, grew k and n by the same amount. We doubled both. However, what matters is the relative size of k and n. And so we actually grew k relative to n. You could think about repeating this over and over and over again. Eventually, k and n are going to be kind of on the same order. They'll just differ by their initial differing amount. And so in that case, they'll kind of converge in their size. And so then k would be, on the polynomial scale, very close to n. It'd be like at least n to the 0.0999, whatever. Or sorry, 0.999. Okay. Cool. So that explains this part of the diagram. And so then the final full description of the reduction is everything that we already said. So just to recap, change the distribution using the distributional map phi, clone and symmetrize. Okay, then we have to fill in the diagonals because they just had nothing there. And so we better put something there. And then we permute the columns. And now finally, if we want to move to a different point in the parameter space that has a bigger k and a weaker signal, we can do this cloning where we turn each entry into 4. And we just check that it indeed moves us in the correct region of, in the correct direction of the hard triangle. So the question?
Very first step, we need to do it lambda like times √2 or something to account for the cloning that we'll do later, or if this somehow not matter.
Sorry. I'm not sure I totally understood your question, but I should have emphasized. So this cloning is only moving us a minuscule amount along this trajectory. So really you have to repeat this some constant times log n times to move appreciably, because we're trying to move polynomially far away. And at this point, we've only changed all the parameters by a factor of 2. We're actually trying to change the exponent in the polynomial. Right, so we repeat this some number times log n number of times. And then we'll get 2 to that number.
Sorry, actually, I think I was referring to the cloning used to remove the symmetry.
Perfect.
So the first step needs lambda √2 instead of that.
Good. So my answer to that is just that I will not care about any polylog factors way back. Wow, it's very far. But when we draw this diagram, we just don't care at all about polylog factors. Yeah. Cool. All right, so the one thing I just didn't explain at all was how in the world this filling in the diagonal thing works. All right, so let's zoom in on the planted submatrix. So this is k by k. Everything here is Gaussian with mean lambda. And maybe again, just to emphasize, the reason why we can analyze the situation that this is precisely the correct distribution, Gaussian with mean lambda and everything else Gaussian with mean 0, is because of this composition lemma that lets us always assume that the input is what we wish it was. Okay, so we have this. This isn't exactly the correct distribution. It would all be blue if it was. And so all the diagonal is purple. And there's a very slick lemma that will just save the day. Okay, and so here's the lemma. So let M be an little m by little m matrix, where each of the diagonal entries is sampled according to P, and each of the other entries is sampled according to Q. Suppose pi is a uniformly random permutation on m elements. And now consider the matrix Mij with a pi up there, whose index ij entry is I, and then you permute the j. So this is really just permuting the columns of matrix M. And so what we have now is that each of these sort of incorrect distributed entries is now in a random location. And so forth. Okay, so this is what this Mij, or maybe I should just call this M pi. Okay, now what the lemma says is that the total variation between the matrix where everything, I should have put a reversed P and Q. Let's reverse them here. That'll be easier. So Q is the diagonal, right? That's the normal 0, 1, and then P is the off diagonal. That's the entire rest of the planet submatrix. Okay, so the lemma says the total variation distance between an M by M matrix where everything is P and this funny permuted thing where we had something that was messed up on the diagonal and then we randomly permuted is bounded by a constant times chi-square divergence between P and Q. What is the chi-square divergence? Well, it doesn't really matter for the purpose of this, except for that it bounds total variation. It's Yeah, it's like a L2 relaxation. It's actually what you get by bounding total variation using Cauchy-Schwarz. But anyway, it's sort of like a probability metric. It's not a probability metric, but it behaves like a distance between P and Q. I can write down explicitly what chi-squared is in a second. But anyway, it's some explicitly computable thing. And for us, that's just going to be a constant times mu squared. And mu here, remember, is like 1 over root log n. So this is going to be like 1 over log n. And in particular, it's going to go to 0. So what's remarkable about this lemma, I mean, it's not that hard to prove, but what's remarkable about the statement is that we're looking at the distance between an entire matrix and another entire matrix. And there's many, many, many entries that aren't what they should be, right? There's m of them. However, the distance here is actually a scalar quantity. It's m independent. It doesn't matter how big this matrix is. This bound on the total variation is the same. So in particular, if P and Q are fairly close, then you're never going to know that the entire diagonal was the wrong thing once the permutation is applied. Okay, so let's see. Do I want to write down what chi-squared is? Maybe I won't, but I'll just say that this is called the Chi-Square Divergence. And you can look it up on Wikipedia. And that actually fully proves that this reduction is doing everything that you wish it was. So with that, I'll take some questions. I do have some backup bonus stuff. If people are interested, I could give a hint about a reduction to sparse PCA. But it's also been a lot of lectures, and so I'm happy to just take questions and end there. So yeah, what are your questions?
So let's first
Yes, please. Yeah.
Yeah, just to be clear, on the last slide, before we do the permutation, we have like total variation distance.
Yeah, great point. Yeah, so before we do this, if you knew that those entries were going to be on the diagonal, then you would just ignore the entire rest of the matrix because you knew that those were sort of correctly matching. And then the total variation, it's actually a priori unclear that it scales linearly in M, but it will certainly grow very quickly with M, at least like root M. It actually sort of depends. Yeah, but yeah, good. Yes, please, yeah.
So is there a reduction in the other direction by clustering?
Yeah, great question. So there's not, and it's a particularly good question because there are actually several reasons why it's strongly believed that there cannot be a reduction in the opposite direction. And I'll say what those are, and then I'll say what there is hope for, what we do have in that kind of flavor, in that vein. Okay, so the reason why it seems extremely unlikely for there to be a reduction in the opposite direction is that there is a quasi-polynomial time algorithm for Planet clique, which is, regardless of how big the clique is, assuming it's polynomially sized, search over size 3 log n subsets. There's not going to be such a big clique in a Erdős-Renyi random graph. The biggest clique is of size 2 log n. So if I find one, then I know I'm in the planted case. And so that takes time, n to the 3 log n times. So it's quasi-polynomial time. Now for biclustering, it's strongly believed that it requires sub-exponential time to solve. And so if there were a reduction, then we'd have a quasi-polynomial time algorithm for biclustering. Okay, so that's maybe one reason why a reduction seems hard. From the technical side, it seems extremely hard to reduce from biclustering and actually to get a clique. So like one natural sort of algorithm that you would do, maybe I don't know if I need to write anything, we'll see. But you could start with the biclustering matrix. You could just threshold everything at 0. So if you do that, then all of the non-planted entries, which were standard Gaussian, become Bernoulli half. All the planted entries become Bernoulli half plus something. So maybe I'll just draw that. So right, so if we threshold, these become Bernoulli half. These become Bernoulli half plus constant times lambda. Okay, so this is a partial answer, which is that this is a sort of trivial reduction that goes to a particular regime of what's called planted dense subgraph, which is just planted clique, except for there's a denser subgraph there instead of a clique. So that's maybe sort of yes, like there's the simple reduction, and these two can actually be shown to be equivalent in a very strong sense. So one can actually map here essentially by the reduction we described. It actually turns out that one doesn't need to start with a clique to map to biclustering. You can start with this thing, this instance of planted dense subgraph. Okay, so those two are equivalent, and that's maybe quite good. But now if you think about mapping first to this planted dense subgraph, it seems very hard to get a clique. We have just a slightly dense subgraph. And to get a clique, you have to be quite confident. This edge is a clique edge, like I should add it. And so if there's any uncertainty at all, then I don't know, if like you're missing one edge in the clique, it's bad news, it's no longer a clique. So anyway, so that seems hard. But there's this sort of partial thing. And maybe along that same vein is one of the big questions that I think I and collaborators and various others are working on is to try to get a bunch of equivalences here. So all of the reductions so far form sort of a directed acyclic graph. So how can we do what's closer to what's done in complexity theory with completeness classes and so forth, and argue that this big set of problems is fully equivalent?
Like I get